And then as a reminder, so today is actually the end of chapter 9. That means Monday and Tuesday are just to review, and then the test for chapter 9 is on Wednesday next week. Yes, Piper. I will be copying them 7th hour. If you stop by, like towards the end of 7th hour after school, I'm not going to have you do it for this one, but I will have the review copied by the end of the day. Okay, so we are solving systems of inequalities today for conic sections. So I need your attention up here, please. I just said I need your attention, so if you didn't hear me say that, it's because you're having a side conversation right now. Solving systems of inequalities that involve conic sections, we will also see, or rather review, absolute value graphs as well. But when graphing these, you can only solve them by graphing. There's two things that make graphing an inequality different from an equation. What are the two things you have to remember with inequalities that don't apply if you have equal signs here? So inequalities, what do you have to remember? You said one earlier, Piper. You have to shade, and then you have to determine if the graph would be solid or dashed. So don't forget to check if something should be dashed before you draw it in. Don't forget to shade. The solution set then is where the shaded regions of both graphs will overlap. So that's what your solution is, and that's why we have to solve these by graphing. So where your graphic organizers are going to be helpful to you is all of the inequalities are given to you in standard form. You will have to decide what conic section it is so that you know what to graph. And then it's just kind of a review of graphing all of the conic sections. There isn't an example of every conic section on here, but we have graphed all 4, so it's just reviewing how to graph those along with absolute value. So for example 1, I'm just going to rewrite this top inequality. We'll work on graphing that one first. So I'm just going to rewrite it here so I can label what this is, label the values that I need from it, and so on. So if you look at the standard form of that inequality, first determine what conic section you have. So would this be a parabola, circle, ellipse, or hyperbola? It is a hyperbola. How would you know that? Yes. So this is in the form that both ellipses and hyperbolas are in, but remember when you have the minus sign, hyperbolas are when the terms are subtracted.
Okay, how do you spell? Because in our sheet it says H-Y-P-E-R. So.
Never noticed that. It should be a P.
Okay, I was just making sure.
Yeah, I never noticed this. This should be hyperbola, not hyperbola. Year 3 of using this, and no student ever pointed that out to me. And I never noticed it. That should be a P. Yes, hyperbola. Saying the wrong thing. Okay, so yes, hyperbola. And then this is good review for your homework quiz, hint on how to graph a hyperbola. So first of all, identify if it's horizontal or vertical. Which one would this be? It is horizontal. Okay, it is a horizontal hyperbola. Now I will say when you're graphing the conic sections for systems of inequalities versus me just asking you to graph a conic section individually, notice I'm not asking you to fill in any blanks of which ordered pairs you're plotting. There's certain parts of the graph that I would normally have you graph if I just wanted you to graph a hyperbola, for example, that you won't be required to graph here. So I'm just looking to see, can you get the curves? All of the characteristics you don't have to write down for me to see those. If it helps you to write them down, you can do that. But if I know this is a horizontal hyperbola, think of how we graphed hyperbolas. I first had you find the center. So we would need to know h and k from the inequality. So what is the center of this hyperbola? 0, 0. H and k based on the x squared and y squared are both 0. So I can plot 0, 0 right away. And then usually we identified A and B, bless you, so that we could find the vertices and the covertices. So what would the A value be for this hyperbola? 2, yes. So the A squared would be the 4, so A is 2. So here normally, and some of you might use the ordered pairs, the formulas, to get the ordered pairs and then plot. Here I would strongly recommend, I'm not making you write down the ordered pairs, that you use the A and the B values as distances to plot the points that you need. So what I mean by that is if my hyperbola is horizontal, I know that A is the distance from the center to a vertex, and I know the vertices would be to the left and to the right of the center if it's horizontal. So I can start at the center and I can go to the left 2 units and put a point that's one vertex, and then I can go to the right 2 units, put a point that's the other vertex. Okay, you don't have to label off to the side what those points are. If you still wanted to use the formulas to find the points and then plot them, you can certainly do that. But it might just be a little bit quicker if you, again, understand that A is the distance from the center to a vertex. And then we need the value of B so we can plot the covertices. What was it? Okay, yep, B squared is 12, so then B would be about 3.5, the square root of 12. Yeah, 3.46 if you rounded to 2 decimal places, or 3.5. Just don't round to a whole number. So then the covertices for a horizontal hyperbola are up and down from the center by a distance of B. So from the center, I can go up 3.5 and put a point, and then down 3.5 and put a point for the covertices. Or again, you could use the formulas to find what they are and then plot them. And then once we had the vertices and covertices plotted, what did we do next to graph the hyperbola? Yep, the dashed line we drew in that box or that rectangle through the vertices and the covertices. After we drew in the box or the rectangle, what did we do? Yep, the dashed lines, the asymptotes that go through the center and through those diagonals of your rectangle. The asymptotes give you the shape of the hyperbola. And then once you have those drawn in here, you just need to make sure then you are graphing the curves of the hyperbola the right way. So remember, this is a horizontal hyperbola, so we should have a curve opening right and a curve opening left. Now, will the curves of the hyperbola be solid or dashed? Solid. So we have a greater than or equal to. So here you need to make sure if it was just greater than or if it was less than, without the equal to, we would have to also dash the curves in. So make sure you pay attention to whether or not it should be dashed. This is solid. But use the asymptotes to draw the curves in. Make sure that the curves do actually go through the vertices. And that would be the graph of the hyperbola. We still will have to shade. Make sure your curves do go through the edges of the coordinate plane, just so you have distinct areas to shade in. And so here's how you shade for a hyperbola. Either you're shading both regions that are on the outsides of the curves, so both of these would be shaded, or everything between the two curves would be shaded. Those are the, I realized for a hyperbola, it looks like there's really 3 regions. The 2 outer regions are one region, and then the region in between the curves is the second. So you can still test a point. I would say 0, 0 is still the easiest to test. Even though the center is 0, 0, the actual hyperbola doesn't go through 0, 0. So you can test it. Or you could pick any point that the actual curves don't touch. So if I test 0, 0, substitute 0 in for x and y, For the x, I would have 0 squared over 4, that's 0, minus, for the y, 0 squared over 12 is still 0. So the left side of that inequality is just going to be 0, and then I have greater than or equal to 1. 0 is not greater than 1, so that's false. So then, if it was true, I would shade everything where 0, 0 is, which is in between. Since it's false, that means I'm shading both outer regions. So both outer regions for that hyperbola should be shaded. And now I realize a hyperbola alone, there's a lot that we just put on this graph, and we still have to put another graph on the same coordinate plane. So this is where having another color pencil or pen, or if you used a pencil, now you use a pen. Somebody did ask in second hour, and this is fine, for the hyperbola, just to take some stuff off of the graph. If you, once the curves are graphed, want to erase all of the dashed asymptotes in the box just so everything in the middle is kind of out of your way, you can do that. You have to leave the curves, but all the dashed stuff you just put in, you could erase if you used pencil, just so there's a little bit less on the graph to see. So we're going to do the same thing for the second conic section. So looking at this standard form, I'm not going to rewrite it. I'll just write information next to it. What is that conic section? Is it a parabola, circle, ellipse, or another hyperbola? Based on the standard form, what would you say that is? The second one. This would be an ellipse because, again, it's that same form that we kind of saw above, except we have x and y added together. So this is an ellipse. Is it a horizontal or vertical ellipse? It is horizontal. Why? Yes, for an ellipse, a squared is the bigger number. Yep, and it's under the x. So that doesn't have to be true for hyperbolas, but it does for ellipses, so this is horizontal. So this is just good review of graphing all of these. So for an ellipse, we find the same information, find the center. So HK, what would the center be for this ellipse? 4, 0. H is positive 4, and then with the y squared, k is 0. So I'm going to plot 4, 0 right away. And then we have a squared and b squared identified. So if a squared is 25, a is 5. So then I'm going to plot the vertices and co-vertices using that same method. A is the distance from the center to a vertex. And if it's horizontal, the vertices are to the left and the right of the center. So I can go from the center left 5 units. I would be at -1, 0. That's one vertex. And then if I go right 5 units, I'd be at 9, 0. That's another vertex. And then since b squared is 16, b is 4, and the co-vertices would be up and down from the center, a distance of b. So I can go up 4 units from the center and be at 4, 4. That's one co-vertex, or down 4 units from the center and be at 4 and -4. That's the other co-vertex. You do not. Oh, I didn't say that for the hyperbolas. Yes. So for the, when you're just graphing a system of inequalities, you don't have to find the foci and plot those. Same for the ellipse. So it's kind of like you need the bare minimum. I just need to see the hyperbola or the ellipse. You don't need to have all the extra stuff when you're doing this type of problem. Otherwise, when you do need it, I'll have the blanks off to the side asking you for it. Okay, and then before we draw this ellipse in, or maybe you already did, should it be solid or dashed? It should be dashed. So if you already drew it in solid, make a note that it should actually be dashed. So the curve you're drawing in for the ellipse through the vertices and co-vertices should be a dashed curve. Okay, there's a lot going on this coordinate plane right now. And then we still need to test a point for the ellipse. So again, 0, 0, so either you're going to be shading inside of the ellipse or everything outside of it. 0, 0 we can still test because the ellipse doesn't go through it. So if I put 0 in for x, inside of that parentheses I would have -4. -4 squared is a positive 16, so this first term would be positive 16/25. You could get a decimal if that's helpful to you. When I put 0 in for the y, I would have 0 over 16, that's just 0. So on the left side I just have 16 over 25, and that is less than 1. Is that true or false? That's true. So therefore I want to shade where 0, 0 is, and that's inside of the ellipse. So for the actual solution to the system, it's where the two shaded regions overlap. So what I'm going to do is shade everything in the ellipse that's already shaded by the hyperbola, which would just be kind of this rightmost part of your ellipse. So to the right, or inside of the ellipse, to the right of the hyperbola curve that you see in the ellipse. And for the solution region, I should be able to easily tell where the solution region is. So either shade it in darker, or shade it in a different color, or highlight it. Yes. Or draw an arrow and say this is where my solution for the entire system is. So any ordered pair in that region would be a solution to the system. Questions at all on example 1? Okay, so then example 2, I included a couple of examples. This example includes an absolute value graph. You've graphed these before. It's been a few chapters since we graphed them, so it's kind of review of graphing absolute value graphs as well. What shape do absolute value graphs have? They have a V, yes. So absolute value graphs, you can identify them because of the absolute value bars. So we'll start out, for example, to graphing the absolute value part of it. And yes, this is going to be a V shape. So the V could be opening up or it could be opening down, kind of like a parabola, but it's a V and not a U. A review of how to graph these. So we just graphed these by making a table, but I always told you it was helpful if you could find where the vertex of that V is. And again, to find that, you take what is in the absolute value bars. So if there was something written outside of these, I would still only take what's in the absolute value bars, and I set that equal to 0. And then I solve that for x, and that gives me the x value of the vertex. So to solve this for x, I would add 4 to each side, so 2x equals 4. Divide both sides by 2. X is 2, so this is the x value of the vertex. That way when I set up my table, I want to then substitute in at least one other x value on either side of 2. So I could do 1 and 3. So you need at least 3 points. You can certainly do more. I would say find the vertex and then do 1 point on either side. And then these all just get substituted into, think of this as an equation, substituted in to find your y value. And remember to take the absolute value of what's in the absolute value bar. So for example, if I substitute in 1, I'd have 2 times 1 is 2, minus 4 is -2, but the absolute value is +2. So that y value would be +2. When I substitute in 2, 2 times 2 is 4, minus 4 is 0, absolute value is still 0. And then when I substitute in 3, 2 times 3 is 6, minus 4 is 2, absolute value is still 2. And with your vertex, the values, just like for a parabola, the values on either side of your vertex, the y values should be the same. So if they are coming out different and you're just getting a line and not a V, it means you either didn't find your vertex correctly or perhaps you're not taking the absolute value correctly when you substitute numbers in. So then I will plot these points, and then when I actually draw the V in, should it be solid or dashed? Solid. This will be a V opening up, solid V. And then we need to shade, and it'll either be shading inside of the V or everything outside of the V. So I can test 0, 0 since that's not on my graph. So if I put 0 in for the X and the Y, I would have 0 is greater than or equal to. Putting 0 in for X would give me 0 minus 4, which is negative 4, but the absolute value is positive 4. So I would get 0 is greater than or equal to 4. That's false. So therefore 0, 0 is on the outside of the V. It's false. I want to shade inside of the V. Okay, and then I have one more graph to make, the second one. Y is less than or equal to negative quantity x minus 2 squared plus 6. So this is not absolute value, no absolute value bars, so identify which conic section it is, parabola, circle, ellipse, hyperbola. This is a parabola. Which way is this parabola opening? Opening down. So that's just helpful to know, so you know which formulas you're looking at if you're trying to identify your H, K, or A values. So here's what you need for a parabola. I realized there was a lot of stuff when I just asked you to graph parabolas. There's a lot of stuff you needed to include. You needed to include the axis of symmetry. You needed to include the focus, the directrix. I had you find the latus rectum. You don't need to find any of that for this type of problem because we're just focused on the solution of the system, not just the graph of the parabola. So all you need for the parabola is identify the vertex and then find 1 point on either side of the vertex. So you need 3 points just like we needed for the absolute value graph. So the vertex is HK, which would be what for this parabola? 2, 6. H would be positive 2 and then K is the plus 6 that's there. So 2, 6, I'll plot that right away. And then just set up a table. Vertex in the middle, you need 1 point on either side. And then since you know the y value should be the same on either side, you really just need to plug one value in. So say I substitute in 1 for x. Here you do need to be careful with the negative that is the a value. So when I substitute in 1, I'm going to have 1 minus 2. That's negative 1. I have to do the negative 1 squared, which is positive 1. This negative in front then makes it negative again. So that all together is negative 1 plus 6 is 5. And I said it was opening down, so if you find when you graph it it's opening up, you know something is incorrect. So I would have 1, 5. That would reflect over to 3, 5. And is the parabola going to be solid or dashed? Solid. And just like the absolute value, I'm either shading everything in the parabola or outside of it. And 0, 0, it does happen to be in the parabola if when you're drawing your curve, you're not sure, you're thinking, well, I know I drew it, so it looks like it's inside. Is it really? Remember, you can always test any other point that you know for sure is in the parabola or for sure outside of it. If you wanted to check, you could even plug 0 in to see if, or to see what the y value is there. It is inside. So if we test 0, 0, we would have 0 is less than or equal to. If we put 0 in for x, we would get 0 minus 2 is negative 2. Negative 2 squared is positive 4, but the negative in front makes it negative 4. Negative 4 plus 6 is 2. So we get 0 is less than or equal to 2. That is true. So that means we would shade where 0, 0 is, which is inside. And so I'm going to shade what's inside of the parabola that's already shaded by the absolute value. So it's what is kind of in between the insides of the parabola and absolute value graph.